All right, so now we go. Any questions about that summary, or we just go to? Yeah, well, maybe it's when we'll come back to all of that later. So now we're gonna start really slow and consider univariant Lagrange interpolation. So this is very familiar to all of you. So if I have a finitely many points, a1 through n, and I assign given values at these points, f of ai, I'm asking for a polynomial of minimal possible degree that takes this value at given points. Then a formula which is called Lagrange interpolation formula, even though this was discovered by somebody else. That's the usual kind of usual story in mathematics and probably also physics. Anyway, it's called Lagrange interpolation formula. It's in front of your eyes. And so it formula actually much better than it seems, because you think about this. It apparently has denominators, but in fact, if which you have poles when points collide. But in fact, if you think about it, there's also the value of the function which have to if the points collide. In other words, if your points collide, you get the derivative. You interpolate not only a function but also some number of its derivatives. So it's all good. It's a formula valid in general, whatever these points ai are. And what this is that interpolation from the locus. So what is this? So this means I have some function prescribed on the locus where x is equal to one of the AIs, and this locus looks like, so if I have 3 points, this locus looks like a little bit what I've drawn here. So so this is the union of, so of course, well, x is equal to one of AIs. Over the space of AIs, it's a union of three hyperplanes, or whatever, n hyperplanes, and these hyperplanes intersect, in a kind of a standard pattern, which for 3 points this is going to look like that. And so you have a function defined on that locus, and you're asking for interpolate to the ambient space. And this is given formula for you right there. So I hope it's non-controversial. So now the same thing. If I'm asking if instead of a fine space, I will be talking about a torus, interpolation of Laurent polynomials. And then I get an extra degree of freedom with that, because Laurent polynomials, I also can, monomials are invertible. And so in my formula, I can, for example, I can, since I'm interpolating at the point AI, I can stick this factor x over AI raised to any power L I want. And the effect of that is that instead of, so previously we were getting a polynomial of degree n, but now, or n minus 1 rather. So previously we were getting polynomial of degree n minus 1, but now we're getting the degree of a Laurent polynomial is degree of Laurent polynomial is not a number. It's rather what people call Newton polygon, means the convex hull of the exponent that entered that entered that polynomial. So it's a polygon in one dimension. It's a segment, and that segment is now allowed to move from some L to some. So it's going to be still the same size, but except the start and the end of that sequence of monomials can be arbitrary. That corresponds to that parameter L. Again, I think there's nothing more to be said about this. And now we come to actually elliptic situation. So now we we were talking about a fine line, then we talked about the torus or the multiplicative group, and now we'll talk about the elliptic curve. And so elliptic curve for us would be, you can talk about general elliptic curves, but for us, we'll take elliptic curves over complex numbers, and those can be written concretely if I take C stars, the non-zero complex numbers, and mod out by powers of Q, where I will assume that Q is less than 1 in absolute value. And so that's an elliptic curve. And then in contrast to so on the torus and on the line, we had natural set of functions, namely we had polynomials, Laurent polynomials, and now on the elliptic curve, we have the natural things to consider are sections of line bundles, and those are on the elliptic curve, a line bundle of degree d can be described concretely. If elliptic curve is written as a quotient, then the line bundle of degree d can can be described as a set of its section could be described as a set of solutions of Q difference equation. Namely, the Q difference equation shown here, where when I take f and multiply x and multiply by q, it produces a factor which is some constant times x to the minus d. That's going to be give you that such a thing will have d zeros on the elliptic curve, so it'll be a section of a line bundle degree d. And what you notice here that this thing has a parameter, namely c, and that c is naturally taken elliptic curve itself, or maybe the dual curve if you pay attention. And so this says that in contrast to what we had before, for polynomials we had no freedom. For Laurent polynomials we had a freedom of where to start, and for elliptic curve we have a freedom which is really continuous moduli for line bundles. And so when we want to interpolate sections of line bundles, well, we'll have to take that into that continuous degree of freedom into account. And so by Riemann-Roch, if I have a line bundle degree d, this will have d sections. And so then it's meaningful to ask is if I can take d-dimensional space of section, interpolate and assign any given values at d given points. And so, well, maybe first I'll talk about what these sections are. Is that so if I have d sections, each one of them, since line boundary degree d has d zeros, which if I denote x1 through xd, then in fact the product of them, or whatever the group operations here, we write the group operation elliptic curve multiplicative. So the group operation applied to that set of zeros of your section, that's going to be some constant. And that constant is, up to normalization, that value c above. So in other words, your the set of sections of your line bundle, this is in fact parameterized by some constant multiple times the product of theta function. Theta function is this remarkable section of degree 1 line bundle that has a 0 at the origin of your elliptic curve. So if you write this expression, that's going to be that's the space of sections of your line bundle, where the xi is multiplied to some fixed constant, which is more or less c before. Maybe call that constant z here. And so then the interpolation problem is when the restriction map. So if I have I have that set, if I'd like to restrict it to the point a1 through ad, whether this map is isomorphism, and it's, well, I mean, if since it's a space between it's a map between two vector spaces of dimension d, so it's an isomorphism if and only if its kernel is empty. And what could be in its kernel? Well, if something is in the kernel, it means a function vanishes at all these points ai, and so it has to be some constant multiple of the product of x of the theta function x over ai. And so this means this happens if and only if that product of ai is in fact z. And so we see that the interpolation problem, you can write a formula. It means it's going to be a formula very close to this Lagrange's interpolation, but it'll be in that variable z will be also an elliptic function, and it will have a pole exactly at this resonant value where the points at which you try to interpolate exactly combine to that parameter z. Right? So that's the shape of the formula, which I think you can all write as an exercise. And now we will revisit. So I hope maybe I spent too much time on these basic things, but also it's good to put us on one page, and so then we can. Now the way we were going to think about this very basic facts is we will interpret that set from which we interpolate. The set is always the same. Set is the union of either hyperplanes or subtori or abelian subvarieties where x is equal to one of the AIs. And so from that set, we interpolate to the ambient vector space or the ambient torus or the ambient product of elliptic curves. And then, and what we were going to interpret that set as the spectrum of the Euclidean cohomology or Euclidean K-theory or Euclidean elliptic cohomology of a very simple algebraic, very, very simple manifold, namely the projective space. And indeed, so, I have to, yeah. And indeed, and And indeed, so sorry, where did I go? Oh, right. So I was going to explain. So sorry, I was going to explain what is K-theory. So I don't mean to insult your intelligence, but I will explain a little bit. I don't want to explain what's a covariant elliptic homology. It's best for you. It's best you actually read the the best paper to read about it is Ginsburg, Kapranova, Serra. I think it's a marvelous exposition. But I will try to explain what's K-theory, and then you can somehow. I think it'll give you enough feeling for the current elliptic homology. And so maybe I'll start from just kind of basic representation theory. And representation theory, the very important thing is like the characters. So we have a representation of a group, we associate its character, which is a function of the group. So namely the trace of an element of a group in the representation. That's a very basic construction. And it is a ring homomorphism with respect to the operations. When you do representations, you can take a direct sum, you can take the tensor product, you can define the ring of virtual representation when you consider the direct difference you introduce formally the operation of direct difference. And so that would be so this map from this representation ring or ring of virtual representation, character is a homomorphism from there to functions on the group. And so, for instance, if our group is, for us, the main group is the torus, and for that the representation ring, well, any monomial can be a character of one-dimensional representation. So the representation ring is just the coordinate ring of that torus, but taken with integral coefficient. So that's the conclusion. And now, if the group acts, the generalization of representation of a group is an action. So representation of a group is an action of a group in a vector space by linear transformation. Instead, you can think of an action of a group on a family of vector spaces parameterized by points of some manifold. And so this means you can think of this group G acting on a vector bundle over some topological space M. And so those are the objects there. So the G, this is called G equivariant vector bundle over M. And this you can make a ring, again, just like representation, by taking the direct sum of bundles, the tensor product, and introducing formally direct difference. And so then would be, this is a very useful ring, and the analog of the character here is, then you should take instead of the action of an element, instead of a trace of an action to define, you have to define a trace, you have to have a vector space. But what you do is that you take the alternating sum of traces of an element on all cohomology of your vector bundle. That's kind of the appropriate thing. And for instance, if the topological space itself is a point, then we're back to the previous definition, namely you get the representation ring of G. Right, so for any topological space with a G action, then we have that very interesting ring, the Kg of M, and its spectrum is generalizes. Its spectrum of that ring is something we're going to be looking at. So for instance, to reinterpret our picture here. So we'll take a one-dimensional torus with coordinate x. So it is the spectrum of the ring where you take Laurent polynomials in x, and we have an n-dimensional torus with coordinates a1 through an. We'll make them act on n-dimensional space, acting diagonally by diagonal matrices, and then you should really think of that Cn as n by 1 matrices, and this is the natural action of something GLN and GL1 on n by 1 matrices. So, and one acts on the one side, the other acts on the other side with the inverse. So this is how this group acts on n-dimensional space. And now the basic fact about covariant K-theory is that if my vector space, it's homotopy invariance in particular, if my vector space if my manifold is a vector space, then it's the same as the K-theory of a point. So if I take integer valued polynomials polynomials with integer coefficients in coordinate x and ai, that is the covariant K-theory G1 cross G2 equivalent key theory of that space Cn. Now the crucial step. If I have a vector bundle on something larger, I can restrict it to something smaller. So there is a map. There is a map from the K theory of Cn to the K theory of Cn minus 0. And so this is it. The rings themselves, they go covariantly. They go contravariantly with the map, but means their spectra will go covariantly with the map. This is here from the larger we restrict to the smaller, means the spectrum of the smaller will embed to the spectrum of the larger. And now when we look at the smaller thing, when I take away the origin, then the group G1 starts acting freely there. So it's and then another basic property of the covariant K theory, that if a group acts freely, then it's the same as the K theory of the quotient. So instead of having G1 equivariant, I can divide by G1, take the quotient by G1 and remove G1 equivariant. Then the quotient of Cn might take away the origin by G1, that's the projective space. And so I get the G2 equivariant K theory of projective space. And that's exactly I claim. So this is exactly the functions on the algebraic variety I described, namely the union of hyperplanes. And to identify, to somehow to convince ourselves that that's exactly the right thing, is that says that well, the only thing which is not an equality in this chain of equalities is the restriction from the open set from the whole space to the open set. And what dies in this restriction is precisely, we throw away the point. The only thing that dies in this restriction is the class of the skyscraper sheaf at that point we remove. And that class of the skyscraper sheaf of the point we remove by Kazul is exactly the product of one minus xi over ai. So that's the Kazul resolution tells you this. And so that says that when I look the dual map and I think the embedding of the spectra, the equation of that will be exactly that. So this means that when the product of 1 minus x over ai equals 0, that is the spectrum of the covariant. That's the image of, you take the spectrum of covariant K theory of projective space and map it to the spectrum of the ambient stack. That makes sense. And so the problem we considered is in fact the following: is that when we have a natural map from the K theory of the ambient stack. What's the K theory of the stack? Just K theory of a stack. It's just G equivalent objects on the pre-quotient. And then there's a restriction to the stable locus, and we consider this gives, so this is the interpolation, and this defines for us the interpolation problem. And we see that in elliptic homology, there's unique, there's unique for every class of line bundle, there's unique lift of equivariant of elliptic homology classes to the ambient stack, which is in that class of a line bundle, it's a meromorphic elliptic. It's an elliptic function, meromorphic function with a pole with certain resonant values, which are very important feature of life. That's any kind of, this is a little bit basic, but important. And any questions about this? All right. So then maybe you can, if you understand this, then maybe in your spare time, or while you're bored listening to other things, you can ponder what's going to happen when instead of I thought you would take Cn is like n by 1 matrices. What if we take n by k matrices and take the quotient by GLK on the one side, on the other side? And then the quotient instead of projective space is the Grassmannian. And then the question is about interpolation. So instead of interpolation, one of a univariate function in x at some point, we now interpolate a symmetric polynomial in some variable sec1 to xk, which is what the cohomology of Grassmannian looks like. And so we interpolate that at the point where we have some collection of n, we have a collection of n variables ai, and we interpolate it at the points where the set of x's is some subset, some distinct subset of distinct elements of A. So that's as silly as it sounds. It actually somehow, in a way, this is the essence of the Schubert calculus, and some you either, if you don't know this, you might enjoy thinking about it. And to bring this closer to the integrals, one way you can see this interpolation problem is that suppose if you want to compute a typical integral in the K-theory of Grassmannian, integral instead of a Euler characteristic type of integral, but also instead of a Riemann integral, a typical integral will be an integral of the form I have this on the slide, where you have some when you're integrating some K-theory class f of x, and there's this kind of weight which is very familiar to everybody who does this kind of gauge theoretic computations. And then what you will notice that if you compute this integral by residues, that the residues will occur exactly at the location where xi's are, well, the poles and denominators are where the xi's are subsets of ai's, but then there's also zeros in the numerator, which force this to be a distinct subset of ai's. And so then you notice that if you want to compute this integral by residues, then you would like to know the values of the function f exactly at the points which I've just had on the previous slide. And so then in particular, if you would like reconstruct what the function f is from its values of somehow pairing with everything else in an integral like that, this is exactly interpolation problem. And so these integrals already look like the integral that we had with that star, with the following differences. Namely, here this is an integral of a rational function, but instead we would like to have an integral that involves Q gamma function. And Q gamma function is well, the way to define Q gamma function is a product like that. And so instead of having a single pole in an integral, it gives a progression, a geometric progression of poles with denominator Q. And hence we would like to interpolate not just at the one point, but in fact a whole sequence of points with differ by powers of Q between them. And this is, you can imagine, this is where elliptic interpolation will be important. And also the way to very quickly explain the need for the Q gamma functions for people who've never seen them is that if instead of doing K theory of some variety x, in fact, I do K theory of polynomials maps from C to X, and it's a space of polynomials with value in X. Then of course I get when I have for polynomials, I have all these coefficients in different powers, and then if I do this this computation equivariantly with respect to the variable Q rotating the source of the map. Remember, in the first transparency, I had the C, and the variable Q was rotating the source of that map C. Then if I do that equivariantly, then the typical computation, if I have maps, like if I have maps from C to C, then that computation would be the Q gamma function. So this is from this one thing is the Q gamma functions, and instead of considering algebraic varieties, we'll be doing maps to algebraic varieties, loops or polynomials with loops or something like that. So loops would be more like elliptic function. This is just polynomials with values in algebraic variety, maps from C to algebraic variety. And then the second thing is that we would like to, generally speaking, people much prefer to have somewhat balanced expressions than where for every Q gamma function in the denominator, there's a balancing thing in the numerator. And for one thing, this is good for like if you want to if you want to have a good limit to Q to 1, then it's this is something very good to have that balancing like that. For example, this ratio of two gamma functions will converge to some more familiar factors, some more familiar functions. And this means to have that balancing means that we instead of having algebraic varieties like Grassmannian, we would like to have, in fact, a symplectic. We would like all varieties to be symplectic. Like so, instead of Grassmannian, we'll take like T star Grassmannian, and that the exact how exactly we balance everything, the numerator is controlled by some parameter h bar, which is analogous to the variable t in this McDonald/Chudnik theory, and it's also that h bar is also the parameter that rotates the algebraic symplectic structure on X, and it's also what rotates the three superior these three hypercalic structures and so forth. And so in terms of in practical terms, that instead of taking a quotient like Grassmannian is a quotient of matrices, JT quotient of matrices by GLK, we would rather think of T star Grassmannian, which is algebraic symplectic reduction of T star matrices by GLK. So that's algebraic symplectic reduction is when you put the complex moment map to 0 and then you take the quotient, take the JT quotient. So now we're going to do this. We'll come to the following setup: is that X will be T star of some M, taking algebraic symplectic reduction by some G. And maybe I'll state from very clearly from the very beginning that this is, of course, a setup very familiar to many of you. Is that in the setting of the original gauge theory problem, so G is the complexification of the gauge group, and T star M is, M is some representation, some meta representation. We would like this representation. In fact, we would like to double it. So we would like this representation to be symplectic. So that's how much supersymmetry we want in this problem. And to record the ambient symmetry, we will fix some bigger group that normalizes G. So it's some part of the normalizer of the group G. Some people say flavor symmetry group. And so now we will study. So now problems that we just considered before, we will now consider in this generality, subject to usual hypothesis that there is in this algebraic symplectic, in this GIT quotient, there are no strictly semi-stable points. It's not. It's more of yeah. Well, anyway, it's something I don't want to deal with right now. So let's just let me make this assumption. And so now the general somehow maybe abstract picture would look very so abstracted things would look very close to this example with projective space. Namely, we have that we have X is a quotient by the group G, and so then there was a group G tilde that was acting, normalizing the action of G. So there'll be G tilde divided by G. That group will continue acting on X, and so in particular X will have a covariant elliptic homology. And for the purposes of this talk, you can imagine that the covariant elliptic homologies you take the covariant K theory, and this is something that sits. So the covariant K theory I explained, this is something that sits in the product of tori, and you just take all this tori, reduce that mod Q, so it will sit in the product of elliptic curves, and so that will be the working definition of recurrent elliptic homology. So recurrent elliptic homology is some scheme. I mean, already also when we take about recurrent elliptic homology, we already talk about. We don't talk about the ring. We just take about this. We don't have a ring, we don't have a spectrum of the ring, but we have a scheme. Like I said, you can take the spectrum of K here and reduce it mod Q. One thing. So this is some scheme which has a finite cover to varying cumulative homological point, similar to in the example with projective space. This will have coordinate x and a1 through an. And subject to condition that x is equal to one of the AIs, and this projects to just the base of given by AIs. So that's the current of a point, and that's in general it's something like this: the finite projection to just a product of elliptic curves, and that sits in some ambient thing which is also a product of elliptic curves, well, modulo Weil group. So the whole thing sits in the current G tilde modulo G elliptic homology of a point that's just a product of elliptic curves modulo the Weil group, and that sits, and then there's a bigger thing which is also product of elliptic curve, also modulo bigger Weil group, and somewhere there is a subvariety that covers the base finite to one, and then what we're asking is for interpolation from that subvariety to ambient space. So just like in projective space, except that the union of the subvarieties is much more complicated, but somehow the setting of the problem is exactly the same. And what we'll remember is that this interpolation, we will do it not for sections of one given line bundle, but in fact all possible line bundles of a certain fixed degree. We'll talk about degree in a second. And so then the line bundles we want, that will be similar like a projective space. When we take projective space, that was a quotient by GL1, and the line bundles on that quotient come from representations of GL1. And similarly, if I have a one-dimensional representation of the group G, then that will give me line bundles on the quotient there. And so then my variable Z will be in fact in characters of G tensor elliptic curve. That's the parameter where the line bundles. That line bundles that I want to interpolate, they're parameterized by objects like that. So that's it's like your it's a bit, it's like well, anyway, so this is what it is. So and the degree that we would like to interpolate is that we would like, so the degree of a line bundle corresponds to codimension of elliptic homology class, and we would like that degree to be kind of middle. Means we would like the elliptic homology class to be like a Lagrangian cycle. Maybe to bring the example of the projective space, we had T star Pn that was that's something 2n dimensional, and then we were interpolating at but with line bundle degree n, the middle degree, and that roughly corresponds to Lagrangian cycles in T star Pn. And additionally, of course, since we would like them to correspond to something on algebraic split reduction, we would like them to be supported onto zero of the moment map. That's the hardest part. So this elliptic homology class has to be supported on zero of the moment map. And so then there's a theorem which is somewhere between hard and not so hard. So I mean, now by today's standards, it seems like it's not such a hard theorem. On the other hand, it generalizes construction. It generalizes many constructions that came before. This existence of stable envelopes, in particular, it generalizes the existence of stable envelopes in K theory, which is at a certain moment in development of science was not so easy to explain. But anyway, the theorem number one says that this interpolation problem I discussed has a unique solution in rational, meaning meromorphic function of variable z, with poles which are kind of interesting subvarieties, interesting divisors in the product, interesting sub-abelian varieties in what parameterizes z. And this is, like I said, this is a generalization of many different things. It generalizes stable envelopes, both in all ordinary homology, current K theory, and current elliptic homology, to this set of group, first elliptic and second kind of non-abelian setting. And that's well, anyway, that's what theorem one says. And now we will now look at this formula that I had before. And so in that formula, we have three things in this integral. One is the stable envelope of beta, means interpolation of elliptic homology class to some elliptic function. Second is the stable envelope of some other class, where in fact in that formula we go to K theory, we set Q equals 0. So and then maybe mnemonically you should think of this as since beta is described at infinity, maybe at the end of the cigar or the kind of boundary of C in some sense, that it takes values in a circle, like a finite size. So there is Q is alive, where alpha is put at the origin. So it sits like on a circle of 0 size. So which is why for alpha we take that Q, set it to 0. And then there's a product of U gamma function that corresponds to the weights of your group acting to the weights, or whatever, to the weights with which the group G rotates the matter and also the gauge fields. And then the theorem 2 is that in fact that is this K-theoretic counts of maps this integral is the K-theoretic counts of maps to X, whatever quasi-maps, or in physics language, this computation of this supersymmetric index, this integral is. And in particular, as a corollary of some work we did with Andrei Smirnov some number of years ago, this integral will solve, for instance, very interesting Q-difference equations, such as Knyzhnik-Zamolodchikov equations or the dynamical equations in quantum groups. So anyway, this is a very long story developed by many people, including Alexander Varchenko, Giovanni Felder, and many people, starting with Rashid Tikin himself, and also big school in Japan for this. So this is I'm a little bit, I'm running out of time, so maybe I won't be able to name every person who contributed to this line of development of solving the Knyzhnik-Zamolodchikov equation by an integral. But that's a certain step which generalizes many previous constructions.
The question.
Sure.
So if there's a pole in the gamma function,
yeah,
do with this contour. The contour is a unit circle.
The contour is just there's no poles. Yeah, that's just contour is just the real torus.
Well, gamma function have a pole, right?
Yeah, but pole is away from this contour. Yeah, we don't.
Oh, but depending on the choice of the parameters.
No, there's no.
There's nowhere there's a pole.
There's no pole of integration here. I mean, there are poles. You can. So this is this. Maybe I should say one thing, that this theorem is proven somehow geometrical. There's no contour deformation, no pole residue, somehow no nothing. But in particular here, in this expression, there's no pole of integration. You could compute it by residues, but that's not what we do.
It depends on A's, right? This Flavor parameters.
It depends on everything. Everything is.
But if it
depends on stability conditions. So like the definition of the stable envelope. Stable envelope is first of all, it's defined in Akrenic homology, in full Akrenic homology, so it corresponds to all flavor variables. But second, it's also interpolation from a stable locus to the ambient stack. So in particular, it depends on the choice of the stability conditions. So that would be, like, for instance, that would be this integral. With this integral, you can say, you can compute the monodromy in one step. It just says the monodromy says the difference of the state. The monodromy says, so in general, kind of the monodromy, people say it's like that. It's like the ratio of two R matrices, of two half. The monodromy is like an R matrix. An R matrix is like the ratio of two stable envelopes, and so that this integral will say the monodromy is the R matrix. But this is there's no poles in here.
Okay. All right.
That helps. So anyway, there's and now I'm a bit out of time, so maybe I will not try to. So I had a few slides. I had a few slides with kind of, so I'm a mathematician, and so when I talk to other mathematicians, I try to explain them what this kind of basic physics is about. But maybe this will be the waste. Maybe this is what I have. 15 minutes. You start 5 minutes. Okay. Well, so this may be right. I apologize to people well versed in theoretical physics for this kind of 25 cents worth of why is it important, why is it interesting to do this sort of thing. Is that the reason? One reason to think about it is that this x can be written as a critical locus of some function that combines both the real and complex moment map divided by the compact subgroup in the group C. So this is the H group, and then you can and so this you can interpret as the Higgs branch of the modular vacuum in a suitable 2+1 dimensional supersymmetric gauge theory, in which volumes we discussed about before, whereas we have the gauge symmetry, which is a compact form of G. There is the larger group divided by this group is the flavor symmetry, and there is a matter representation, which is T star M. And then the maps to the vacuum, so maybe the best explanation for why is it interesting to study maps to the vacuum is this picture of a weather map, because what is weather? Weather gives you like the pressure and temperature. Pressure and temperature are the coordinates on the moduli spaces of Gibbs state or steady states for air. And so this is a weather map is a modulated vacuum is a map to the moduli spaces of vacuum. And then the ones we would like to, if we want to compute an index, we first of all might as well go to this infrared description. So instead of trying to compute the index in a microscopic description of a physical theory, we might as well take this macroscopic description of a physical theory. And second, we might as well, since we have so much supersymmetry at our hands, we might as well use it and compute the index not with all possible maps, but only with the holomorphic maps. So since our moduli space of X is holomorphic, we can study holomorphic maps, and so the compute, and then those now form finite dimensional manifolds we compute some index computation or k-theoretic computation on some finite dimensional, not exactly manifold, maybe some singular, very singular varieties, but we compute, what we really compute is the index of a certain G tilde current index of a certain virtual Dirac operator on modular space of holomorphic map from a Riemann surface to X. And these are very complex, but real computations. And so this means all actors and actresses and the scene of this computation, all of that is defined. I mean, it's mathematical computation. And as I said, this is why people interested in this, because it's a way to access to say something about the full evolution operator in the full 2+1 dimensional gauge theory, and certainly a lot of my colleagues in both the mathematics and physics think about it. And so many of them are at IPMU and elsewhere. And the most important geometry here in this setting, C is in our hands, and also the index we computed currently with respect to both the automorphisms of X and the curve C. And so the most important curve C, I mean, any kind of physics, the most important geometry is the flat space. And so if one can take that source to be the flat space, just make the normal italic C, we can take it to be the blackboard C, and then accept that to work on this, to do the index computation in such non-compact geometry, we need to do it currently, like Nekrasov taught all of us. And so then, so that the setting I discussed on the first slide is that we have our space-time is a flat two-dimensional space across a circle in time, and we have a covariance which acts on the space by rotation and on X, however it acts. And then there are two fixed points. There are two fixed points of rotation in space, the origin and infinity, and we insert two things there. And we can compute that, and the result is what I said it is. And the fact that something like this solves a Q difference equation, that's on kind of a formal geometric ground. It always does. This is like the analog of Q analog of the Brovin connection from the quantum. I mean, this is like the sister. It's like K-theoretic sister or K-theoretic brother of quantum cohomology. So that's this, more or less the same argument. More or less the same argument as quantum cohomology proves that there's some difference equation here. And this is it's a separate story to identify that difference equation, but the fact that it is there is a fact. And a basic fact about this, I mean, somehow maybe one kind of basic fact about one basic historical fact about this is the following: is that if I have this object, so let me come back here. Okay, So this object, this solves Q-difference equation in all variables, all variables in the problem, every single variable, and it solves a Q-difference equation. And so, in fact, you have not one Q-difference equation, but a whole system of commuting Q-difference equations, compatible Q-difference connections. And then, and in particular, if you set Q to 1, this will be a whole bunch of commuting matrices. And by the kind of computation which is by essentially saddle point computations in the integrals which we considered here, maybe less so maybe I'll let me since I have time, so maybe look at this expression here. So if I look at this expression here and I set Q to 1, then nothing particularly bad is going to happen to the stable envelope. Stable envelopes are somehow slightly insensitive to that. What is going to blow up is the gamma function. And so then, so this is any kind of rough saddle point analysis of this integral. So if you have it's not, like I said, I mean, not so important what are the insertions, but if Q to 1, you get the saddle point analysis of that integral will tell you you have to look at the asymptotics of the gamma function. And so then what you will see is that and what Nekrasov and Tshidashvili saw many years ago is that the equations you get they have the form of beta equations from kind of familiar theory of quantum integral system, and so hence they conjecture that this whole theory should be solvable in the language of certain quantum groups. And what this actual integral that I've displayed, that is in some sense culmination of all that theory of quantum groups, because this is not only you construct first of all, you need to construct certain quantum groups, means you have to construct them geometrically via some procedure, first constructing the braiding and so forth. That's through this machinery of stable envelopes. And then one kind of identifies the corresponding Q-difference equation as the equations that are intrinsic to the theory of quantum groups, namely the Knizhnik-Zamolodchikov equation, the dynamical equations, and related equations. And then, and so this integral in some sense summarizes, since you have a solution of this integral equation, summarizes in some sense, beta ansatz, it's about diagonalizing the matrices that you get from this at Q equals 1, and but it's also well understood point that if you can solve an inhomogeneous equation, if you can solve QKZ and other equations, and actually solve that by an integral, that in particular gives you solution of the beta ansatz. So in particular, the stable envelopes you see in this integral, those are the off-shell beta functions, and that's another way to that's another name that is relevant here. And so and then there's certainly like a million other things I could have said and stressed many other connections with other parts of mathematics, in particular those mathematics and physics, in particular those developed at IPMU. But it is now, I think, by my watch is exactly 12:30, so maybe it's 12:30 in Moscow, so it must be 16 or whatever, however, maybe. So we're 6:30 in Tokyo, and so maybe it is time for me to stop and take questions if there are any.
Thank you very much for very clear talk. So, any question or comment?
Andrei, hello. Hello. Might ask maybe a naive question. Is there a sense or a way to substitute the K-theory classes by derived categories? I thought on physical side there are certain obstacles to do so. Is this question sensible mathematically?
Could you ask it again? What were derived categories or what?
Substitute K-theory classes by derived categories.
No, all this computation makes sense. In fact, they make sense in the kind of derived category. So this is maybe I don't want to take words out of Misha's mouth, but you should really study that in like elliptic homology should be it's like the K-theory of coherent sheaves on loops to X, and you can set up the problem and study that in that generality, like elliptic, like elliptic. Certainly ordinary K-theoretic stable envelopes, they can be categorified, and I think the elliptic ones can be also categorified. So it's totally it's totally reasonable to expect that in fact there is a categorification of this equality here. So this would be in particular that this would mean that it will only not give you not just the kind of this virtual class computation as a computation case here, but actual homology classes. So that's, but we did, so with a student of mine, we did it for like small degree for T star P1, it works. But I know it's T star P1 is it's like the SL2. If something works for SL2, it's promising, but to get from SL2 to E8, it's a long way. So.
Okay, Masahito.
Oh, okay. So you discussed the interpolation problem on the elliptic curve. So can you generalize the problem to higher genus Riemann surface with their higher genus Taylor functions, etc. So and then try to solve the interpolation problem.
Sure. I mean, this is yeah, from kind of purely algebraic geometry. From kind of pure algebraic geometry viewpoint, there's no reason not to do that. I wouldn't know how to use topological kind of ideas for this, because maybe it's not the question exactly to me. Is that like, where to put this kind of Jacobians of other algebraic curves, where to put them in the topological situation? Maybe you can ask Misha. Yeah, I'm not exactly. The point here is that we don't use algebraic. I mean, I don't use algebraic geometry to attack that problem directly. I mean, the problem is that the problem is solved by some topological arguments. So then you, but it's I'm not sure where that. I've been asking myself all the time too. Since there's so many nice special functions, why can't we use topology to handle all of them? But that's like I said, you have right there. They're much better topologists than I, so you can ask him.
Okay, yeah, let me ask him then. Yes.
Yeah.
Okay, next Samuel Murphy.
Yeah, thank you. I had you mentioned this balancing condition that you have to put in a function of h bar. Now, is h bar an infinitesimal variable or is it a finite variable? In other words, when you say gamma of h bar, do you mean really the function or an asymptotic expansion?
No, it's an actual variable. Yeah, this is so this is the h bar is a variable in the torus. So all this this integral that I have here, it is an integral on the compact torus, but all the functions involved are meromorphic on the whole torus. So it's so that's and h bar is a variable in the torus, just like all other variables.
I see. So
because h bar is just an equivalent variable that so this is a little bit. I know this is a little bit. It is somewhat confusing because it's there's like in QKZ there is this shift. People usually consider QKZ at like level 1, where the parameter of the quantum group and the shift are actually equal,
right,
or maybe up to a power. And so, but here, if you think about QKZ abstractly, there's no need for this. The parameter of the quantum group is one variable that's denoted by h bar, and that's that is geometrical. That corresponds to the fact that if I think of my varieties, if I have my x coming from T star M, then there is a symmetry that just scales the cotangent direction with some weight h bar. So that's a symmetry of the theory that rotates the 3 hyperkähler structure, and that becomes the parameter of the quantum group. So if we forget that h bar, then we get that from instead of a quantum group, we get the ordinary kind of loop algebra. And that's, I mean, also very interesting, but it's not, has nothing to do. I mean, it's a different. H bar is parameter of deformation in a quantum group away from the classical situation. On the other hand, the other variable q, which also has a meaning, also has a meaning from the point of q special functions. And I think the point I was trying to make is that the analogy here should be maybe like if you think of Magdalene theory has q and t. So q is like q and t is like h bar.
I see. So q is not e to the h bar. It's a completely different variable.
It's not. It's a different thing. Yes, exactly.
Thank you. Sorry.
Sure.
Okay, next up here.
You mentioned that these gamma q's have poles in Z and they have an enumerative meaning as scalar roots. How would a physicist interpret these enumerative things? Is that?
Oh, so this is the stable envelope. So okay, so maybe I'll come back to that. Yeah, the theorem one. So you have some interpolation problem, and you know that this is solution is going to be meromorphic function of Z, and then with some poles. And so what are those poles? Those poles are the following. If in this, now without any kind of Q difference and so forth situation, you can do just like the quantum cohomology effects. And the quantum cohomology effects, you have like Kähler variables, which are also Z, because Z also come from Z is the same kind of thing. So this will be computation in quantum cohomology effects with some series in Z, and that series will be rational function with some poles, and that those poles are the poles are the same. So that's kind of the fact that this series in fact sum up to a rational function with poles. It's a somewhat special situation. I mean, in general, if I study quantum cohomology of, I don't know, whatever, something which is not constrained by very, very kind of rigid supersymmetry I have here, then it'll be some special function, we know with no particular properties, no known radius of convergence and so forth. But here it sums up to a rational function, and in fact the poles of that rational function have a kind of a deep meaning, in particular as poles in this whatever quantum differential equations or some other resonant this resonant loci, they have a very interesting interpretation.
I have like two more very slight naive question. So in the integration of this main expression that you wrote down with the this one right here, the contour that you've chosen it such that there are no poles inside this contour. But what prevents us from deforming to a contour that actually does contain a pole? And if you do that, what happens?
Yeah, well, that's exactly this. So you should ask Hori-san about it, because this is exactly what people
related to what he asked. Yeah.
This is exactly what people kind of do all the time, meaning they write, so they analyze the sort of problems by deforming contours, picking up residues. And in fact, if you look at like Nekrasov paper, Nekrasov papers, they also write a contour integral, deform it, pick up residues, and so forth. Whereas, of course, I mean, there's different geometric language which will say that these two expressions are equal without this sort of manipulation, but you can certainly do it. And in fact, if you go to this, if you go to the first slide, there's a reference, a paper on which this talk is based, and then that paper is specifically to help people digest the geometric argument. Also wrote a translation for the Grassmannian. What does it mean in terms of like contour deformation and so forth? But the advantage of the more geometric language, I think, is that you don't have to think about poles and residues. I think it depends. I mean, if it's in example, I think it's easier to think about kind of contours and residues and so forth. But in abstractly, I find it difficult. I find it easier to well, I mean, it depends. I mean, it depends on, it's very, very background dependent. But I do find it easier to think about more geometric arguments rather than contour deformations. And and residue computation. But in principle, of course, since they both relate to the same quantity, they in the end they're the same. This is not what I use, even though I mean to help people digest the kind of argument I give is I wrote down the translation for specific case of Grassmannian, which is very, in some sense, very basic case. Since as Nakajima varieties go, you can't have any smaller quiver that there is for Grassmannian. But so that's it.
Anyway. One more question. I think at the start of the talk or towards the end of your elevator pitch, you mentioned there are some deep number theoretic connections. Could you maybe elaborate on that too, please?
Oh,
or maybe you could do it like later too, like next Japanese class.
Yeah, like let's have a discussion. I love to have a discussion for that. That's maybe.
Okay, then we talk after Japanese class.
Maybe right now this connection is too deep for me. Maybe a little later I'll have a better way to explaining it.
Yeah, sorry, I just have one more follow-up. So if I am brash enough to do this quantum deformation and pick up the poles and everything, am I trying to interpret this change in the integral as some sort of a wall crossing formula in the quantum elliptic homology, or what? Is that a wrong interpretation?
Yeah, you can do so. What you can, right. It's like saying exactly. I mean, you're right. I mean, there's something like it's like so. Right now I think my current thinking about this elliptic homology is like an interface. I mean, sorry, stable envelopes. Stable envelopes like an interface, meaning you have some external variables. In this case, maybe stability condition. So you have, and then in your space, you can have a situation where you have that stability condition actually kind of varies in space, right? And so you can have a situation where you have one stability condition on one side of a certain boundary, and then another on the other side of the boundary, and then maybe zero on the right. So this means I forgot what. Sorry, I'm blanking what the things are called, but it's well, what they call it, FI parameters or something like that. And so you can have them vanish at some codimension one thing in your space, and then you should have an interface between. So the stable envelope is really an interface between the situation when you have a stability condition and we don't have stability condition, or you have a zero stability condition. And then the R matrix is when you go from whatever positive stability condition to a negative stability condition. And so that sort of thing you can analyze kind of hands off, which is what I'm trying to do. But you can also do it kind of hands on with actually analyzing. And so I believe there's in particular work of Mykola Didushenko with Nikita about some kind of hands-on approach to this. So maybe this is something something that could be useful for you to look at. And so one possibility.
Okay, thanks.
Okay, Melissa, do you have a question?
Oh, yeah. So you talk about like stability conditions. Can you say how this integral depends on like the stability condition of the GIT quotient?
Right. So this again, the stable envelope is some interpolation problem, right? So you take, well, let's do T star. Let's do T star P. Let's do T star Pn example. For one stability condition, is the spectrum of elliptic homologies where X is equal to one of the AIs. And then for the other stability, for the opposite stability condition, is when X is equal to something like H bar times AI. Because the space and the dual space have exchanged their roles. And so then you have inside your ambient stack, you have inside your ambient stack, you have the spectra for elliptic homology for both X and the flope of X. And so you're interpolating from one, or you're interpolating from the other. And if you want to go from one to the other, then what you do is you take a function of one, interpolate, restrict to the other. And there's the consequences of this formula that says that this would be the monodromy of the quantum difference equation.
Thanks.
Sure.
Okay, any other question? I don't see hands.
I have a question.
Yes.
I believe this is somewhat a generalization or related to a generalization of your work with Maulik, relating equivalent cohomology of moduli space of instantons to some affine Yangians. So the quantum group here, can it be thought of as some kind of Yangian?
Right. So this is the there are two quantum groups here. One is the Q difference equation is written in terms of like QQ of GLN one hand hat for this. So this works for arbitrary quiver and many other things, but so for a quiver, so for maybe the quiver, the Jordan quiver was one vertex and one loop. Then the quantum group that we had with Davesh was the Yangian of GL1 head. To talk about the Q difference equations and so forth, this would be UQ of GL1 head, or sorry, UH bar. Sorry, I'm contradicting myself. The UH bar of GL1 head. But then the monodromy, so this will give you the Knizhnik-Zamolodchikov, and the statement would be that there's this Knizhnik-Zamolodchikov equation, and the actual quantum difference equation would be this dynamical equation for UH bar of GL1 head. And then the monodromy of this equation, so if you take quantized loops, the monodromy of the corresponding Q difference equation, that is traditionally associated with the elliptic quantum group. And indeed, here we would, like, if we talk about the monodromy, which means to change of the stable envelopes, the one which is, so there are two stable envelopes. One corresponds to UQ, so one corresponds to Q equals 0, another corresponds to live Q, and so the ones, if I change one or the other, I'm gonna get in one case the R metrics for UQ, sorry, UH bar. I keep saying this. One give me UH bar, and the other will give me elliptic R metric. So the monodromy of things related to UH bar of some loop group, that would be the corresponding elliptic group. Again, it's a well understood thing, and then this is I mean, except it's very hard to prove, and so the easiest proof I know is that through the kind of argument that I didn't exactly explain, but you can find in the paper.
Okay. Thank you.
Okay, any other questions? Okay, let's thank Andrei again.
Thanks, everybody.